So welcome everybody. Just for the people who were not there yesterday, perhaps Praneeth is currently a research scientist at Google Research, and he's been telling us about gradient descent. And today, I guess we're moving from independent samples to dependent data. So over to you, Praneeth.
So yeah, so thanks again for coming to the second talk. I would like to maybe continue on the talk that I gave yesterday, which was about broadly about stochastic gradient descent. And yesterday we spoke about how to do acceleration in the stochastic setting, and what are the challenges, and what are the algorithmic ideas that we can use to speed it up, do acceleration in the stochastic setting. And today I would like to take a slightly different aspect within stochastic gradient descent, which is about learning or optimization with dependent data. Okay, and yeah, so this is joint work with again a bunch of amazing collaborators: Naman Agarwal, Shumantak Chaudhary, Prateek Jain, Suhas Kaushik, and Dheeraj Nagaraj. So again, if there is any question, like please feel free to stop me and ask me right away. Yeah. Okay. So yeah, so there'll be hopefully this will not be too repetitive, but because like there's a 24-hour gap between yesterday and today, I just want to again give a little bit of introduction. So as we saw also yesterday, so we said that optimization is indeed an important component of large-scale machine learning, and a lot of most of the optimization problems that we encounter will be of the following form, where we want to minimize a loss function L of W over W, and the loss function is defined usually as an expectation over some data points distributed according to some distribution phi, and there is a loss function for each data point x. Okay, and we can think of, so yesterday for example we thought of the setting where the loss function L is the square loss, and that was the stochastic linear regression problem. And again we are given only t examples, x1 x2 all the way up to xt, which are sampled from pi. So here I'm using the notation xi, but in terms of yesterday's notation, it would, for example, include xi comma yi, right? So I'm just using xi to make it to keep the notation simpler. And also, as we saw, stochastic gradient descent is indeed the most popular workhorse for solving these kind of problems. And the idea is that given a data point xt, and with the current iterate wt minus 1, you set wt to be wt minus 1 minus a step size eta times the gradient with respect to the xth data point, its loss function on wt minus 1. Okay, so this is stochastic gradient descent. And as we have already seen yesterday as well, so SGD is very well studied, especially when XT are independently sampled from pi. This was the setting that we considered yesterday. And the key property, as we also saw, was that that makes SGD work in this setting is that if you look at the conditional expectation of the gradient of the xth loss function with respect to at wt minus 1, conditioned on all the past iterates, including like all the way up to wt minus 1, is nothing but the gradient of the what is called the population loss function, which is the expected value of L when we take the expectation over xt. Okay, so this is the key property satisfied by stochastic gradients in the independent setting, and this is the property that is used when we want to show convergence of the stochastic gradient descent algorithm. Okay, and yeah, so a key consequence. So the reason why this SGD crucially relies on this property is that under this condition, we see that the expected value of the next iterate wt is nothing but the gradient descent update taken at wt minus 1. Okay, so what it means is that in expectation, SGD is doing nothing but gradient descent, and we can again use the ideas on the convergence of gradient descent to argue about the convergence of stochastic gradient descent. And as we also saw yesterday, tight convergence bounds are known, and we also know of like accelerated methods and so on in this context. However, when xt are dependent, meaning that the samples xt are not independently drawn from the distribution pi, for example, but maybe they're evolving as a Markov chain, for example, right? So in this setting, this is no longer true. And in particular, this talk, we want to understand what happens if x1, x2, all these iterates are the samples are coming from a Markov chain with some stationary distribution pi, but they're not independent samples. Okay, and in this context, we can certainly store all the samples offline and then use an offline algorithm to minimize the loss function. But in the context of big data sets, a offline algorithm is often not feasible. So we are interested in designing stochastic algorithms which can work with this kind of data without having to store all the data points. Okay, and there have been prior results on this problem. And the main issue with prior results is that either they show asymptotic guarantees or they are like the existing results are suboptimal by mixing time factors. So let me try to illustrate this a bit more concretely. And in order to do that, I'll introduce the, I'll first describe what I mean by mixing time. So is there any question until this point? Okay, so I'll go ahead. Right. So let me begin by introducing what's a mixing time of a Markov chain. So let's say Z1, Z2 all the way like is evolving as a Markov chain, right? And let's say pi is its stationary distribution. So the mixing time tau max is defined as the smallest t such that for any starting state Z1, the distribution of ZT conditioned on the initial state Z1 being equal to Z is close to the stationary distribution pi in total variation distance by at most say 1 over 4. Again, this 1 over 4 is there is nothing important about this constant 1 over 4. We can replace this by any other constants, and in general, the resulting tau mix parameter is only logarithmically dependent on the resulting like the constant that you put here. Okay, so the mixing time is basically says that irrespective of which starting state you start in, the eventual distribution after t time steps is going to be close to the stationary distribution by say a factor of 1 over 4. Okay, and what this tells us is that it tells us how fast the Markov chain actually forgets initial condition, because the eventual distribution is going to be very similar to pi. So it actually does not matter whether the initial state started from Z or some other value Z prime. So this is the reason mixing time also tells us how fast the Markov chain forgets the initial conditions. Okay. So let's look at an example of a setting where we would like to do SGD or optimization with data that is actually coming from some kind of a Markov chain. Okay, so the example that I would like to introduce is the problem of learning a linear dynamical system where xt plus 1 evolves as a star times xt plus epsilon t. So here xt is the observation that we make, and epsilon t is a random zero mean noise conditioned on all of the past, and a star is a matrix that we would like to estimate. Okay, so the task is that we are given x1, x2 all the way up to xt, and from the single trajectory we want to estimate a star. Okay. So any question about the problem of learning a linear dynamical system? Okay, so we can pose it as an optimization problem, again a linear least squares regression problem, where we would like to minimize over all the matrices A of the loss function, which is where xt is sampled from the stationary distribution, and we would like to minimize xt plus 1 minus axt square and then take the expectation as xt is drawn from the stationary distribution pi. Okay, and in practice this can be also written as because we don't have access to the exact expectation, but rather we get samples from a single trajectory, we can also write it as the empirical sum of these things, where the empirical sum is taken over all the samples that we have observed in the given trajectory. So we have 1 over t summation t equal to 1 to t norm xt plus 1 minus axt square. Okay, and once we see this, we can directly now try to apply SGD, for example, where we take AT to be AT minus 1 minus the step size times the gradient, which turns out to be given by this quantity. Okay. However, in this case, if we take these samples xt in the forward order as the sequence of observations that arrive to us, then it turns out that stochastic gradient is no longer unbiased and it's actually biased. In particular, the expected value of this given AT minus 1 is not necessarily equal to the true gradient at AT minus 1. Okay, and the key reason is that AT minus 1 actually depends on all the things in the past, including x1, x2, all the way up to xt. right? And these things further correlate with the xt and xt plus 1 that we are currently using from the current data sample in order to estimate the gradient. And because of this correlation, the conditional expectation of this thing given at minus 1 is not the true gradient of the original loss function here that we would like to estimate, right? And consequently, stochastic gradient descent does not work properly on this problem. So hopefully this makes it clear why stochastic gradient descent does not work when we have data that is not independent, but rather comes from, say, a Markov chain. And this also illustrates the need for a different algorithm, which can, which is still streaming in the sense that it does something similar to stochastic gradient descent, but still actually does the right thing and not what SGD does. Any question?
So hey, Praneeth, so I guess the single trajectory is the difficult, like, as in you can't wait, like you can't just leave out a batch of samples, say proportional to the mixing time, and then pick the next one.
Right. Yeah, so that's a good point. So let me come there. Right. Okay. So in the previous slide,
I guess motivated by Sid, I was going to ask the same. So in this case, can you show that if you use xt minus 1 into, is the bias somehow related to the mixing rate, sort of time, rate of mixing?
That's a good question. I'm not sure if it may be, in the sense that the mixing time is given by the spectral radius of this matrix.
Right.
Or like the inverse of the spectral radius of like 1 over 1 minus the spectral radius of this matrix. And if yeah, actually I don't see a clear relation, because like the bias here may actually depend even on like the entire spectrum and how this evolves and so on, but the mixing time only depends on 1 over 1 minus the spectral radius. Yeah. So getting back to Siddharth's question, it is indeed possible that you just drop, you take only one every atomic samples and they are approximately independent, and then you only use them to do the estimation. But as we saw in the previous, yesterday's talk also, the final error that you are going to get is going to depend on the number of samples you are able to use. So in the second term, it was of the order of 1 over n, right, where n is the number of samples you have taken. And if you are going to throw away like most of the samples, meaning that you're going to use only 1 over atomic fraction of the samples, then the convergence rate that you are going to get will be off or will suffer at least, will grow only as atomics over n. It will not go down as 1 over n, right? So the question would be whether you can still design okay, and if you solve this problem, which is the offline problem, then you don't suffer that. So from an information theoretic point of view, if I give you n samples, there is no reason for you to suffer this mixing time factor. But when we are doing stochastic gradient descent by dropping most of the samples, then you are suffering that atomics factor. So the question is, can you still design a streaming algorithm which does not lose that atomics factor? Is the point clear? Hello?
Yeah.
Yes.
Okay.
And like, just to like add to my intuition, it's not possible to learn pi as such because its support is huge.
Correct. That's correct. We are only given samples and we would like to just use the samples. And like we only care about learning A star. We don't necessarily have to learn the distribution, which may be much harder.
Right. And you are also not allowed like parallel trajectories, as in you can't run parallel copies of the Markov chain and sort of mix and match. It's just a single trajectory.
So this is a single thing. So this will be the harder case, but if you are able to solve this harder case, then we'll be able to design algorithms which can work in
right,
like with a combination of like a single trajectory of certain length, but then multiple trajectories of as well.
Okay.
Yeah. Thanks for the questions. So yeah, so the idea that we propose is what we call reverse experience replay, and the main idea is the following. So this basically describes the algorithmic idea that we are proposing. So the samples are like evolve in the forward order, meaning that this is sample number 1, this is 2, 3, 4, and so on. So the samples are evolving like this, and the way we use the samples is the following. that we first take a buffer of a certain size. I'll explain like what should be the size of the buffer. But given a buffer size, we process the examples in the reverse order. So we'll store all these examples, and then we'll do SGD in the reverse order. So we'll first do SGD using this sample, then we'll do SGD using this sample, then we'll do SGD using this sample, all the way till the beginning. Once we have processed this buffer, then we leave a gap in the middle, and then we go to the next buffer, and then we again process it in the reverse order. And once we process this buffer, we again leave a gap here, and then go to the end of the next buffer and process it, and similarly. So is the main idea clear? The algorithm for reverse experience replay? Okay. So let me explain like maybe the two key things. So the first thing is that we will be leaving a gap between two buffers of the order of mixing time, right? So that, as Siddharth just mentioned, we can be sure that the samples in buffer 1 and buffer 2 are pretty much independent because of the mixing time guarantee of the Markov chain, right? So the gap will be, so we are indeed throwing away atomic samples in the middle, right? As long as each buffer is of size tau-mix, then we are only throwing away constant factor of the samples, and we will not be suffering, we will be suffering only constant factors in terms of sample complexity, and we'll be using at least a constant fraction of the samples, right? So in order for this, what that means is that we'll take the gap size to be mixing time, like around the mixing time number, and similarly the buffer will be at least the mixing time number, so that we'll be throwing away only a constant fraction of the samples, and the buffer size can be much larger, but all we need is that we need the buffer size to be at least a mixing time. And if we think about it, the mixing time can be actually much smaller compared to the total number of samples, right? For example, in order to get a reasonable estimate, we might have the total number of samples to be dependent on to scale linearly with the dimension, whereas mixing time can be independent of the dimension, right? So the buffer size can be much smaller than the total number of samples. The second thing is that this is not a completely streaming algorithm, in the sense that the memory requirement of this does not scale in terms of single sample storage, but rather depends on the size of a entire buffer, because we will store the entire buffer and then process the examples in the reverse order, right? So the key thing that we are saying is that we are going to relax on the memory requirement of SGD by increasing the memory requirement from O of 1 samples to buffer size samples, which is of order mixing time. So mixing time number of samples. And once we do this, we will see later that we will be able to get statistically near optimal results, while SGD cannot achieve similar results. Okay, and I would like to mention that empirically experience replay has been a very widely used technique, both in particularly in reinforcement, a single trajectory of examples. And while the way that people use experience replay in reinforcement learning is slightly different, and there are also quite a few variants. The reverse experience replay variant in particular has been proposed in this prior paper by Rotinov, and it has shown that reverse experience replay indeed has very good empirical performance. And our work kind of tries to give a more theoretically sound basis for why it works, and how we can try to analyze reverse experience replay in this context. Okay. So let me explain why stochastic gradient descent with reverse experience replay can actually learn linear dynamical systems. Okay. So the main idea is that we have xt plus 1, which is right. So this is just the definition of the linear dynamical system, where xt plus 1 is a star xt plus epsilon t. And we have also said that the expected value of epsilon t, the noise vector given x1 to xt, is equal to 0, right? And when we process the examples in the reverse order, so the way the algorithm looks like is the following. So we have we start with an a0, right? And then a1 is a0 minus a step size times the gradient of the stochastic gradient of the loss function, computed based on these last two samples, xb minus 1 and xb, and that's given by this. And then we get a1, and then from a1 we look at xb minus 1, xb minus 2, and then compute the stochastic gradient at a1, and then we do stochastic gradient at a1. And similarly, we just keep going all the way up to these examples, and then we'll get the final iterate of the first buffer, which is AB. And then buffer will end at this point, end of buffer 1, right? And then we leave a gap of mixing time number of samples, and then we go to buffer 2, right? Now we get AB plus 1 to be the gradient descent at AB, where we use the stochastic gradient computed using these two samples, which are the end of buffer 2, right? So that will be 2B plus Tom x. So this is Tom x, and this is B, and this is B. So this is 2B plus Tom x, which is this going to be this sample, and then the previous one, 2B plus Tom x minus 1. And then we keep processing these samples, and then we get A. So this should be A to B. So, and then we get A to B. And then, so as I mentioned, like the memory requirement here is going to be the total buffer length, which is B samples. Okay. So any question about how the algorithm works?
Hey, Praneeth, I hope like you'll speak to this, like the reverse order, the intuition behind this reverse order later.
Yeah. I'll get to the proof where the reverse order kind of presents itself naturally.
Okay. But is the intuition that for initial steps you want better quality samples, and hence
the intuition is more that there is a particular kind of dependent structure, particularly coming from this epsilon t, that
right.
It's independent of the entire past, right? But it's not independent of the future.
Okay.
So that's the key property that motivates this reverse order processing.
Okay.
Yeah. But I'll come to this in a bit more detail in the later slides. Yeah.
Sure.
Okay, sounds good. Yeah, thank you. So, right. So let me describe our results first. So in the context of learning linear dynamical systems, what we can say is that, yeah, so this is just the setting that I have already described. And the only additional condition that I'm assuming here is that in addition to being zero mean, we assume that epsilon t is actually also sub-Gaussian, or like in this case normal, but it can also be extended to sub-Gaussian distributions with variance sigma square. And then we also assume that the operator norm of A star is less than 1, which is required for stability. And under these conditions, what we can show is that with T samples, right? So if A hat is the output of the SGD-RER algorithm, then the operator norm of the difference between A hat and A star is at most a constant times square root of D sigma square divided by the minimum singular value of the Gramian matrix. I'll again describe what this is, times T. So D here is the dimension of the vectors that we are looking at. D is the dimension of xt. Sigma square is the sub-Gaussian parameter of the noise at every step epsilon t. And the Gramian matrix G is nothing but the covariance matrix of XX transpose. So if we draw X from the stationary distribution of this linear dynamical system, then the covariance matrix of the resulting vector X is what is called the Gramian of this matrix. And the error basically is in the operator norm is given by D sigma square over sigma min of G times T entire square root. And while this looks somewhat complicated, the important point to note here is that this is information theoretically optimal, and we cannot do better than this rate under these same assumptions. Okay. So what this means is that the algorithm that we are proposing is indeed close to optimal. I mean, I'm not saying exactly optimal because there are some log factors that I'm not including here. But apart from the logarithmic factors, this upper bound tells us that SGD-RER actually achieves the information theoretically optimal rate. And in fact, we can also extend this to nonlinear dynamical systems where instead of xt plus 1 being A star times xt, we can have an element-wise nonlinearity applied to this vector. And there are again certain assumptions on the nonlinearity that it has to be monotonic and so on. But in this nonlinear dynamical system setting as well, it turns out that SGD-RER can actually be shown to have information theoretically optimal rates. And for this setting, it's actually the first streaming algorithm that has been shown to work. Okay. So this is the first result on learning linear dynamical systems. And the second one that I want to mention is about Q learning in the context of reinforcement learning, again with reverse experience replay. And just to give a bit of background, Q learning is one of the most popular algorithms for doing reinforcement learning, but it has convergence issues even for simple problems with function approximation. Okay. And in practice, Q learning is actually used with two additional ingredients. And the first one is what is called online target learning, which again I'll explain in a bit more detail in later slides. And then the second one is experience replay. Okay. There has been prior work which has shown why online target learning can actually yield stability for Q learning, whereas like even more earlier work has shown that it actually has convergence issues even for simple problems. So there has been some work which showed that how online target learning can actually fix these convergence issues to some extent. However, there has been no analysis of experience replay. So our result has been the first rigorous analysis of Q learning with reverse experience replay. And we do this in the context of linear MDPs and also obtain finite sample guarantees. Okay. So in the second half of the talk, I'll go into a bit more detail about the setting of Q learning, reinforcement learning, and also about linear MDPs and our result here. Okay. So hopefully the results are clear. Any questions about the results themselves before I go into like the main ideas of the proof?
So when you say streaming, you mean you're only storing something like capital B times the dimension. That's
correct. That's correct. That's correct.
Okay.
Yeah.
And like maybe I'm jumping ahead, but is it interesting to actually save on this? Like instead of storing the vectors, you store projections or some sketches and then use that. Is that something like, because the vanilla SGD would be just order D, like you just it's completely streaming. You don't store anything, but is that a useful direction to think about?
I think that will be useful. Maybe at least certainly for linear learning linear problems, which is like most of our theory is for linear problems. Actually, sketching might yield further improvements. Yeah, that's an interesting question. We haven't looked at that.
Okay. Okay. Thanks.
Yeah. So in practice, I guess like the buffer size is important because even like when people apply this in like the practical Q learning setting and so on, like the buffer sizes are extremely large, and like if you can sometimes like it's just a memory requirement that basically limits how much buffer size you can actually maintain and so on. So yeah, minimizing the buffer size is of interest from this point of view.
Right. Yeah, the memory requirement.
Yeah, exactly. Right.
Okay, thanks.
Thank you. Yeah. Okay. So let me give the general framework of our results, which is what we use to prove both like the linear dynamical system ideas, and then like there is also further work that needs to be done for RL. But again, like the high level ideas behind like reverse experience replay are kind of quite similar. So the setting is as follows. We have like a Markov chain evolving as x1, x2, all the way up to xt. And then we also have these noise vectors, epsilon1 all the way up to epsilon t minus 1. And what we observe is that we have yt, which is a linear function of xt plus this noise. Okay, so yt is w star. So there exists a vector w star such that yt is equal to w star transpose xt plus epsilon t, where the epsilon t is conditionally zero mean and its variance is bounded by sigma square. Okay. And as I mentioned, the Markov chain actually evolves both on x1 epsilon 1 all the way to x2 epsilon 2 and so on. Okay. And the linear dynamical system example, for instance, has the form xt plus 1 is a star xt plus epsilon t. So here it's not a scalar observation, but rather a vector observation. But this can again be put in exactly the same format as long as we make yt to be a vector and w star to be a matrix. Okay. And the second point to note is that in the linear dynamical system setting, both of these properties are indeed satisfied because x2 depends on x1 epsilon 1, and similarly xt depends on xt minus 1, epsilon t minus 1, and so on. Okay. So let's look at a brief overview of the proof when we have the independent setting. So how do we prove the convergence of stochastic gradient descent? So we first have let's go line by line. So Wt plus 1 is given by Wt minus the step size times the stochastic gradient, right? This is stochastic gradient. And we just subtract W star from both the left hand side and the right hand side, just to make it a recursion on the distance from the optimum, right? So we have this equation, and when we know that Yt is actually given by W star xt plus epsilon t, and then we replace Yt in the value of the stochastic gradient, and then we do some simplification, and then what we get is this equation here, which is Wt plus 1 minus W star, which is the distance to the optimum, is satisfies this recursion where we have distance at t plus 1 is some matrix which seems to be smaller than identity, and hopefully this will be contracting, times the previous error plus a zero mean noise. Okay, so when we expand this further to the next time step t minus 1, what we get is we have like two contracting matrices hitting like the previous Wt minus 1 minus W star, and then one contracting matrix hitting the error at the epsilon t minus 1 xt minus 1, and then this error which is epsilon t xt, right? And the key point here is that epsilon t minus 1 and epsilon t are actually zero mean given the xt minus 1, xt and so on. So because we are talking about the independent setting, right, where these are all independently sampled, and so the expectation of epsilon t given like any of the x's is just equal to 0. So once this is true, then both of these become zero mean. So so both of these become zero means, and this is actually a geometrically decaying term because we would hope that this part concentrates around the Hessian. So I minus eta h is actually a matrix whose eigenvalues are all strictly smaller than 1. So we hope that this is geometrically decaying term. Okay. So at least in terms of expectation, we see that this actually converges to 0. And it turns out that right. So we see that the expectation of the distance to the optimum is actually converging to 0, especially when expected value of xt transpose is a full rank matrix. And as I mentioned, like this can be seen using the spectral decomposition of expected value of xt transpose, because this basically decomposes along all the eigen directions. Okay. Now, even though this is zero mean, we would like to understand what's the variance of this quantity. And in order to compute that, we can again go back to this equation and compute Wt plus 1 minus W star times its transpose and then the expected value. So that will be the covariance matrix of this thing. That will involve the covariance matrix at time t minus 1 and then other quantities that arise from here, right? And when we write down what we get, we see that sigma t plus 1 is expected value of some seems like contracting matrices which are sandwiching sigma t plus a additional noise term which depends on the step size eta. And we can also obtain a similar expansion for the average iterate. And if we choose the eta appropriately, then it can be shown that this entire thing actually goes down as 1 over t. The covariance matrix of this, the iterate goes down as 1 over t. Okay. However, the key challenge, so the key thing that we have assumed is that at least the expectation is correct because both of these terms are zero mean, right? But when we have this Markov chain structure, what happens is that this quantity is no longer zero mean, okay? Because epsilon t minus 1 indeed influences what the next xt is going to be, because xt epsilon t is dependent on xt minus 1 epsilon t minus 1. So even though epsilon t minus 1 is conditionally zero mean depending all the way up to xt minus 1, it's not zero mean when you condition it on xt. This is the key reason why stochastic gradient descent becomes biased when we process the examples in the forward order. However, when what we can observe is that if we replace xt transpose with xt minus 2 xt minus 2 transpose, which is the example which was seen before xt minus 1 epsilon t minus 1, then this is actually mean 0 because epsilon t minus 1 was conditionally zero mean, conditioned on like all of the past, right? So as long as we can put an example from the past here, this will still be zero mean. Okay. And what this means is that the analysis in each buffer can then be carried out similar to the independent setting once we have this zero mean property. Okay. And once we have the gap between two different buffers to be at least a mixing time factor, then the successive buffers are almost independent. And the reason this is still interesting is that the buffer size can be much smaller compared to the ambient dimension. Okay, and this is also what makes it challenging, because the buffer size is not large enough that the covariance matrix within each buffer by itself, it cannot approximate the entire covariance matrix of the distribution, right? Because B can be much smaller than the dimension, and in that case, this matrix can never be full rank. Whereas all the algorithm is seeing is only examples in a single buffer at any given point of time, right? So in order for this, analysis still needs to capture the effect of multiple buffers, but the benefit or the key thing that we can use here, there are two key things that we can use here. First is that within each buffer, we can try to do SGD kind of analysis, and across buffers, because we are giving a gap of atomics, we can treat them as being independent and then somehow accumulate the effect of using samples across different buffers. Okay. So at this point, I'm happy to take any questions about the idea behind reverse experience replay, and like why reverse makes sense compared to the forward order, and how the analysis proceeds, at least at this level. Okay, sounds good. So in the remaining 20 minutes, so I hope to give like a brief primer on reinforcement learning and how this arises, how optimization with like correlated data or this Markov chain data arises in reinforcement learning, and how reverse experience replay can again solve this situation. Okay. So okay, so let me first explain the setting of reinforcement learning. So we have a Markov decision process with states denoted by little s and actions denoted by little a. And a Markov decision process basically is defined by the probability transition matrix, which gives us both the next state as well as the reward. So given a current state st equal to s, and the current action that we are going to take at equal to a, the probability transition function tells us what is the likelihood of ending up in the next state s prime, as well as observing a reward r. Okay, so this transition defines the Markov decision process, and we given a Markov decision process like that, so a policy sigma is a function which takes a state and an action pair and gives the probability of choosing this particular action when we are in that particular state. Okay, so this is again a Markov policy in the sense that the probability of choosing an action depends only on the depend on the like the previous trajectory of where I have come from and so on. So a policy for every given state, the policy can be thought of as a probability distribution over all the available actions at that state. And what we would like to do given such a Markov decision process is to maximize the cumulative reward, which is given by summation over t, gamma to the t rt, where rt is the reward observed at time step t, and gamma is a given discount factor. Okay.
Praneeth, are you speaking? I'm not able to hear you.
Hello.
Yeah. I think we lost you for the last 30 seconds or something.
Okay. So maybe was the definition of MDP clear? At what point?
I heard until the policy where this is a probability and a cumulative reward until that point. And
okay. Yeah. So the policy, as I mentioned, as I was describing, is a probability distribution for every given state. It's a probability distribution over the set of actions that are available at that state, and cumulative reward is the summation over all the time steps t of gamma to the t, where gamma is a discount factor which is smaller than 1, times the reward that's observed at time step t. And for any given policy, there is a corresponding cumulative reward. And the goal here is to find a policy sigma which maximizes this cumulative reward. Okay. So we want, for every state, we want to find a policy probability distribution over actions, which eventually leads us to the maximum achievable reward. Okay. So one way to, there are a few important related quantities that help us in doing this optimization, and one of them is the Q value function. Okay. So what the Q value function says is that, so it's a function that takes a state action pair to a real number, and what it says is that if I were to start at this particular state action pair, then what's the maximum expected reward by following any policy, where I'm maximizing over all possible policies, but it's just that I'm starting at this given state action pair. Okay. And one of the fundamental results going back to Bellman is that there exists a single optimal Q star value function which satisfies the Bellman optimality equation. What it says is that given a state action pair, the optimal Q star satisfies the following equation, where Q star of SA is equal to the expected reward that you're going to get because of this transition. And then in the next, so when you take a probability distribution over the next state that you're going to go to, which is S prime, then when you take a maximum over all the Q star values for various A prime, then the sum of both of these quantities on the right hand side is equal to the left hand side. And a Q value function is optimal, meaning that it gives us the optimal Q star value function if and only if it satisfies the Bellman equation. Okay. And secondly, this can also be translated into the policy world, meaning that a policy sigma is optimal if and only if it's induced by the the optimal Q star value function. Okay. Which means that the support of the optimal policy function is contained within the argmax of the Q star of S comma action space, where we take the argmax over all the action space. Okay. And Q learning is basically trying to iteratively solve the Bellman equation, because if we solve the Bellman equation, then we can find the optimal policy using this Bellman theorem. And Bellman theorem also guarantees us that there exists a unique Q star value function which satisfies the Bellman equation. So Q learning is just finding optimal policy by finding the optimal Q value function by trying to solve this fixed point equation. Okay. So this is what is done by Bellman iteration, and the Bellman iteration is the following. So we start with a Q0, and then we update using the right. So we put in the Q0 on the right hand side, right, and then we get a we can evaluate this right hand side, and then we call that Qt plus 1. Okay. And then we put Qt plus 1 again on this right hand side, and then we can get Qt plus 2 and so on. Right. And it is well known, and again, like goes back to Bellman's theorem, that if we do this kind of Bellman iteration, then in the infinity norm, where the infinity norm is taken over all state action pairs, right? If you think of this as a vector in the mod S mod A times mod A dimensional space, then the distance to the optimum, so Qt plus 1 minus Q star in this infinity norm, goes down by at least a factor of 1 minus gamma every time you do this iteration. Okay. So if we are able to do the Bellman iteration, then given Qt, we are able to compute Qt plus 1, and then Bellman's theorem tells us that this converges to the optimal Q star function in this infinity norm. Okay. So the second thing to note is that in order to do Bellman iteration, this actually boils down to a supervised learning problem, in the sense that for every S comma A, we have a right hand side here, right? We can compute this quantity by doing a transition from S comma A, and we want to find Qt plus 1 that actually satisfies this equation. Okay. So in that sense, this boils down to a supervised learning problem. Okay. So so far we have thought about settings where S comma A are discrete, and we have been thinking of these in the infinite dimensional spaces, finite dimensional spaces. But in general, we have these S comma A dimension to be extremely large. So usually we want to do some kind of function approximation. What we mean by that is that instead of denoting each S comma A pair as a separate dimension, we will encoded by using some kind of feature vector phi of s comma a, which will be in say d dimensions. Okay, and we if we can approximate the q value function qt at any s comma a as the inner product between the feature vector at s comma a times some vector wt. This is called linear function approximation, where we are trying to approximate the q value function qt using a linear function. Okay. In this context, Bellman iteration turns out to be a linear regression problem where we are trying to find a vector wt plus 1 such that phi transpose wt plus 1 is approximately equal to this expectation where we have wt on the right hand side, and we want this to hold for every s comma a, right? And that's the reason we are saying that if we are given wt, we can evaluate the right hand side by using transitions from the MDP and then use it to evaluate wt plus 1 on the left hand side, and that's why this boils down to a supervised learning problem. And the online target learning idea is basically that we update wt plus 1 as so when we are doing stochastic, so when we are trying to estimate wt plus 1, so we don't do this for every iteration. So whenever we have a state action pair, we would like to try to estimate wt plus 1 by putting wt here. So we don't update wt to be wt plus 1 at every after looking at every sample, but rather we have batches of samples, and for a batch of samples we will use the same wt as the target network, use all of those samples to solve for wt plus 1, which is the online network. And after the batch of samples is processed, we'll use wt plus 1 on the right hand side, and then again estimate wt plus 2 on the left hand side. Okay. Okay. So again, it turns out that linear function approximation by itself has several negative results, in the sense that q-learning does not converge, and it can be unstable and does not go anywhere and so on. So for q-learning to work, there have been specific classes of problems on which people have shown that sample efficient learning is possible with function approximation. And one of the most well-known classes among them is the class of linear MDPs, where for every given state action pair, we have this feature vector phi of s comma a, but for every state, we also have a feature vector psi of s, and the probability transition function is itself linear. So probability of st plus 1 is s prime, given the current state action pair is an inner product between phi of s comma a transpose times c of s prime, psi of s prime. Okay. And the second assumption we would like to make about the MDP is that so when it turns out that for linear MDPs, we can show that linear functions are indeed closed under Bellman iteration, meaning that if we put a linear function on the left hand side, there exists. So we put any linear function w on the right hand side, then there exists a u which satisfies on the left hand side, which satisfies this equation. Okay. So in this context, so a Bellman iteration basically then boils down to realizable or well specified linear regression, because indeed there exists a u for which this right hand side can be satisfied as a linear regression problem. Okay. So the setting is follows. So we are given samples SA, R, S prime from a fixed expression policy, and then we want to find Q star. So the idea is the following. So we start with a Q0, and we want to solve, implement Bellman iteration on Qt to obtain Qt plus 1. And we do this by solving Bellman iteration using SGD reverse experience replay, and then we repeat this process until convergence. Okay. And yeah, so in comparison to prior work, q-learning had been thoroughly analyzed only for the tabular setting, and even there the sample complexity was not optimal. So our result has been able to extend this result to linear MDPs, as well as improve the sample complexity of the results for the tabular setting as well. So tabular is where each state action pair is considered as a different dimension. Okay. So the main result is that after n number of samples, after looking at a number of samples, the infinity norm error between the estimated q hat and the true q star goes down as 1 over square root n, where there is additional dependencies on two different parameters. So one is gamma, which is the discount factor. The other one is kappa, which is kind of the condition number that we saw in the linear regression problem yesterday, but also has to account for the difference between like the exploration policy and how well the exploration policy visits all the different directions of the state space and so on. Okay. So one important point to note here is that even though the mixing time of the policy comes up in the size of the buffer size, or the Markov chain actually comes up in the buffer size requirement in terms of memory requirement, it actually plays no role in the eventual rate of convergence. Okay. So I will just maybe show some empirical results before concluding. So both of these plots are for comparing SGD with reverse experience replay with other algorithms. So the left plot is for nonlinear dynamical system, and the green algorithm is SGD with reverse experience replay, and all of the other algorithms are either SGD or SGD with vanilla experience replay, where the sample examples are random from within the buffer. And we can see that SGD with reverse experience replay has a much faster rate of convergence and achieves like the statistical limit much faster compared to the offline algorithm, which is this GLM prop. Okay. On the right hand side, we have the results for Q-learning, where the blue one is our eventual algorithm, which includes both the online target learning as well as reverse experience replay for the Q-learning part. And we can see that compared to vanilla Q-learning, as well as using vanilla experience replay, where we only sample randomly from within each buffer, we see that we achieve a much better, we are able to find a policy which is much closer to the optimum than both of the other algorithmic ideas. So to summarize, I want to end by saying that we have considered both nonlinear dynamical systems as well as the problem of Q-learning for linear MDPs. And in the problem of nonlinear dynamical systems, the task is to learn the matrix A star that's driving the system from a single trajectory of observations. And here, sigma can be an element-wise monotonic function. And even in this case, it turns out that SGD with reverse experience replay achieves the optimal statistical rates of estimation on A star. And in the context of Q-learning for linear MDPs, the task is to learn the optimal Q-value function using a given exploration policy. And we obtain the first result for obtaining a non-asymptotic convergence rate for Q-learning using both online target learning as well as reverse experience replay beyond the tabular setting in the linear function approximation setting. So that's all I wanted to say. I'm happy to take any further questions now.
Nice. I don't see any questions in the chat. Questions? Please go ahead. So I have a very nice question. I mean, I wanted to sort of understand a little bit better what you meant when you said that achieves optimal statistical rates of estimation. Are you saying that the dependence on the D's and the sigma mean, those and the T, that is, so which of these dependencies are you talking about in terms of optimality?
All of them, actually.
All of them.
Yeah. Asymptotically, as n goes to infinity, you cannot get better than this.
Achha.
Yeah. So there are some additional terms that I have not written. So for small n, there are some additional terms, but they will become lower order when n goes to infinity. So they're more like 1 over n and so on. So if you look at the asymptotically dominant terms, these are information theoretically optimal.
Questions? I guess we did have a bunch of questions to get on.
Yeah. All right. Yeah.
Okay then. Thank you. Thanks. Let's thank Praneeth for the amazing talk. Very nice. Thank you so much, Praneeth.